So welcome to the functional data structures lecture. So today we swapped. I will give the lecture. Probably I will also give the tutorial. So today it's about priority queues. And who knows the heap data structure from, say, heap sort or whatsoever? Okay, so we will do a similar thing, a heap, but we will do it functionally. So first of all, we need some abstract interface for priority queues. So we just want to have a collection of some elements. Each element has a priority, and the operations are, well, insert an element and remove the element with the least priority, or with the highest priority. We will do with the least priority. So we need the empty queue, of course. We need to test whether the queue is empty. We need an insert operation. And we need, well, return the element with a minimum priority. That's the operations we are interested in. We also want to remove it. So we can either have one operation that retrieves the minimal element and the priority queue with the element removed, or we can split it into two operations. Get the minimum element and remove it. The split into two is a bit easier to handle because we don't return a tuple, but that's it. And we will make one simplification here. We don't have elements that are somehow associated with a priority, but we say the elements are the priorities. So the elements are linearly ordered, and we always remove the least element. So that's just a simplification. Otherwise, one would have to pass this priority queue a function to compute the priority from an element, or a function to compare two elements, or something like this. Any questions to the informal interface of a priority queue? Okay. So we want to have multisets, so we want to allow the same element to be in the queue multiple times. So we use multisets as we did for sorting. Okay, so you should know the multiset. Now let's do the implementation formally. So yeah, we need some type A of priorities that is linearly ordered. And well, then we need some implementation type Q for the queue. We need an empty operation. It returns a queue. Is empty. It queries whether the queue is empty. Insert. Clear what it does. Get the minimum element. Well, this will return an element. It will return an element even for the empty queue, but you don't know which one. So you don't know anything about the element. If you put it on the empty queue, well, it will return something. Isabel functions are total, but you don't know what it will return. Yeah?
And why not use option?
Just to make it easier to use. So if you know that the queue is not empty, you can just write empty and do not have to write the empty or something like this. You can just write get min and do not need to write the get min or something like this. It just makes things easier when you know that the queue is non-empty. Otherwise, it makes no sense getting the minimal element anyway. So it's more like as imagine that the implementation would raise an exception at this point and not return none. That's a better match for this implementation. Okay, and delete min exactly the same, and also, of course, the queue must be non-empty here. And there's another option, merge, that is quite common because it can be efficiently implemented for many functional data structures. So there are even functional data structures that can implement merge in constant time. And merge is just join two priority queues, so form the union of two priority queues. And there's another option that you often see in priority queues, and it's called decrease key. And this means some element that you know that is in the priority queue that you can somehow reference to decrease its priority or change its priority. This is an operation that's required, for example, who knows Dijkstra's algorithm. So if Dijkstra's algorithm finds a new shorter path to a node, it has to decrease this node's priority. So it manages priority queue of nodes, and at some point it sees, I have a shorter path to this node, then it decreases this priority. It decreases this node's priority. So in our simplified setting, decrease key cannot be really implemented because we don't have keys to reference to elements in the priority queue. We just identified elements of the priority queue and priorities. So the decrease key operation is not really meaningful. The only thing you could do here is you could remove, we cannot remove elements. We can only remove the minimum element. So what you could perhaps do in this simplified setting is you could implement a remove some element from the queue operation. But for the data structures that we discuss, this operation will not be efficient. So we don't handle it here. So of course we need an abstraction function. So what is the multiset represented by the priority queue implementation? And we need an invariant. So what is the invariant of the priority queue data structure that we use? We are still at the abstract interface, so we are not looking at some concrete data structure, but we want the possibility to have an invariant. If we don't have one, well, we set it to true. Okay, and now what is the correctness? So the abstraction of the empty priority queue is the empty multiset. Is empty returns whether the abstraction of the queue is actually empty. Insert, as expected, it inserts the abstraction of insertion is the abstraction of the original set with the element inserted. So for delete minimum, well, we need the additional precondition that the queue is not empty. I have swapped an H and a Q, sorry for that. Strange. Yeah, I thought this this slide is generated from an Isabel theorem. So these sort of things should not happen. No, it's not. I have somehow assembled this precondition here. Okay, so this should be, of course, Q.
It should be MZ.
Yes, I probably picked a wrong theorem here to get the precondition from. So it should be MZQ not empty, and under this precondition, well, if I delete the minimum element, then and abstract from it, so I delete and then abstract, then I get the multiset of the original queue minus the minimum element of the multiset of the original queue. And this min m set, well, it's just the minimal element of a multiset. You can define that. So if you have a linearly ordered multiset, you can define what is its uniquely defined minimal element. Because it's a linear linear order and multisets are finite, in particular multisets represented by Qs, there's no problem in defining that. For infinite, yes?
Why do we need a precondition here? Is the Delman function on on the priority queue not handling?
We do not. I put the precondition here to not require delmin to check whether the queue is empty or not, because if the queue is empty, it makes no sense to delete a minimal element because there is none. So of course we could totalize this function by just querying is empty and then returning the identity, so returning the same queue, but I intentionally put this invariant here such that some potential user of this interface realizes, well, perhaps it makes no sense to delete the minimum of an empty queue. And with the still with the same invariant, with the same precondition here, getMin is of course the minimum element of the multiset. So as long as this multiset is finite and linearly ordered, there's no problem in defining this. And this will be the case for all our implementations. So the minimum in Isabelle actually is only defined for, I'm not sure whether it's for all, no, they derive it from a lattice, so they derive it from the infimum of a lattice. So you also have the minimum for infinite sets, but only if they form lattices that have this minimum. So, for example, if you have a set So let's consider, for example, this set. This set, let's assume integers. Does this set have a minimum? Obviously not. But if we would start at -3 here, well, the set can be infinite but still has a minimum, but it has no maximum. But in case of finite sets of integers or finite sets of any other linearly ordered thing, we always have a minimum. We can just compare finitely many elements and pick the minimal one. So that's, and the definition of minimum in Isabelle, well, as long as the set has a minimum, it's well defined, otherwise you just have no lemmas to reason about it. Okay. And of course, last but not least, the invariance must be preserved. So these are the operations that return new queues, and they must preserve the invariance. Everything with a precondition that the invariant holds initially. Okay, so that's the abstract priority queue interface. Any questions to that? So the files should be in the material folder, the accompanying Isabelle theories. Okay. So now we have set the field for priority queues. Let's consider what is a heap. So intuitively a heap, well, it's one part of what you know from heap sort, namely you have the minimum element at the root, and for each subtree the root node is the minimum element of its subtree. So you have something like, let's say we have this this would be a heap. So the root is the smallest element of everything. The 2 is smaller than these 2. The 3 is smaller than these 2. That's a heap. And, well, of course, if you have a heap, the getmin operation is easy. You just return the root node of the heap. It's always a minimum element. The other operations, well, this depends on how you implement the heap. So, well, let's do it. The empty operation is, of course, the empty tree. Is empty? Well, you can query whether the tree is empty. Getmin, yeah, as I said, just return the root of the tree. Now, yeah, let's do it this way around. Assume we already have a merge function. If you have a merge function, so to join two heaps, then we can implement the other functions on top of it. So we can implement insert just by merging a singleton heap with a other heap, and we can also implement delete min. How would you implement delete min? Yeah?
Merge the two subtrees.
Yes. So we can just merge the two subtrees. This effectively removes the root element, which is the minimum. So if we have merge for a heap data structure, we are done. So the most interesting function is merge. We can try to do it naively. Let's try to do it naively on heaps. So we have two heaps. They have elements A and B. How would you merge them? We just want to have it a heap, not worry about balancedness for now. Yeah? Okay, so we put the smaller one to the root, we have min heaps.
Yeah, then
So we put A to the root.
and then depending on, let's assume A will be bigger, then
No, I have A smaller.
okay, then B bigger.
Yeah.
So then we can merge like the two subtrees of B. Yeah, T3 and T4, we can merge these two.
So we want T3 and T4, yeah?
Yeah, and this result we will merge with the whole tree with A and B1. I think that would be possible. I'm not really sure if this is best.
So we want to merge this one. Hmm? So A must go to the top.
Yeah, okay, then I was wrong. I had to merge B1 and B2, and then we merge the whole thing with this.
So you want to merge
B1, B2.
T1 and T2, put it here, and
Would be
put B here.
yeah.
But if you merge T1 and T2, you also get a root element there, right?
Well, we get a new tree, right? So merge takes two heaps and gives you a new tree, and we can just use the tree as a new left successor, and we can use the whole tree starting with B as a right successor. That's it. So may produce very unbalanced trees, but it preserves the heap property because A is smaller than all of these elements, and by transitivity, A is smaller than B is smaller than all of these elements. So we can put both under A. So these are the easy cases if we have leaves, and this is the case that we just had, and the other one. Any questions? Okay. Well, as I said, if we merge naively, well, we may get, in worst case, we get lists, not trees. So it's not that hard to do a merge that produces something like and always having a leaf here. So it's not an efficient data structure. We could have used lists in the first place and would have saved all the storage for the extra leaves. So we have, of course, as for search trees, we have to maintain balance. So for search trees, we used what did we have? Red-black trees, 2-3 trees to maintain balance. So we somehow annotated the nodes with some extra information that we could then use to maintain the balance. We can do something similar here, and we will have 3 heap data structures. Only 2 of them are on the slides. The next one probably will be next lecture. So we will do leftist heaps. We will do so-called brown trees. These are 2 quite simple ways of managing balance. And then we will do the well-known binomial heaps next lecture. They are a bit more sophisticated. Okay, so leftist heap and bound trees are not that well known. Who knows this data structure already? I did not know them. One knows them, okay. Or is it a question? Okay. So for leftist heaps, so we have it's somewhere in material. It should be under leftist heaps. Okay, and what is the idea? So we define the rank of a tree to be the depth of the rightmost leaf. So we have some arbitrary tree data structure. Like this, then the rank of this tree is the depth of the rightmost leaf. So how deep is the rightmost leaf? So it's depending on how we define it, 2 or 1. Probably we can say it's 1, 2. To be honest, I have to look at the definition before I fix to 2 or 1 here. So it's 1, let's say it's 2. The rank of this is 2. The rank of this subtree is 1. So it's always you go from the root to the rightmost leaf, and that's the rank. So that's just a definition. Now we say a leftist tree, the rank of every left child is greater than the rank of its right sibling. So for any pair of siblings here, the rank of this one must be greater than or equal the rank of this one. And here too. So this is actually a leftist tree. It's not very balanced. I can even enlarge it arbitrarily large here. But it has this property that the rank that's the rank of the right to the right, I always have short paths. So that's the problem. So I can append much more nodes here. I can say, okay, well, let's have a leaf here and some more nodes here and so on. Still a leftist tree. But from any node in this tree, the path to the right leaf is short. Actually, it's logarithmically short in the size of the tree. Because, well, I always know when I go to the right that I have more on the left, so to speak. And that's, we will prove that this holds. But the idea is paths to the right are short. So what can we do if we want to do operations? Well, in a heap, the ordering of the subtrees is irrelevant. It does not matter. For search tree, we had always where the smaller elements were here, the larger elements were on the other side. But for a heap, the smallest element is here, and we only know everything below is larger. So if you have a heap like this, T1 and T2, well, we can swap these two. No, we can swap these two subtrees. We can swap left and right here. It's still a heap with the same meaning. Or if we look for a point to insert, for a root node to insert an element, you can go to the right and insert it here instead of going to the left. So that's roughly the idea why for a heap it's enough to have short paths to one side. Okay. Yeah. So this is it. So whenever we insert something, we do it on the right, and whenever the rank of the right child gets too large, well, we just swap left and right, and condition restored. Condition was the rank of the left must be greater than the rank of the right. So we insert something on the right. If the rank, so we insert here, this tree gets bigger, bigger, bigger. At some point it's bigger. If the rank is higher than this tree, then we just swap the two trees to restore the leftist heap condition. And swapping two subtrees, well, it does not, it remains a heap with the same meaning. So that's the rough intuitive ideas. So in order to do that, we have to store the rank with a tree, with a node. So each node gets an extra field, it's this one here, and it stores the rank of the node. Otherwise, it's just a normal tree. And we use this age or rank or height here, but this should be R for rank as abbreviation. Okay. Abstraction is no problem. It's exactly the same as we would have for trees that do not store the rank. We just ignore the rank information. Okay. The heap property, well, that's the standard heap property. It says we had it already. So it says that both children are heaps and the element at the root. The element at the root is smaller than all elements x in the children. Okay, then we need the property for a leftist heap, for a leftist tree. So we need a rank function. So we can define the rank function just as this. So the rank of the leaf is 0, and the rank of a node is the rank of its right child plus 1, which count how often we have to go to the right until we reach a leaf.
Aren't we storing the rank in the constructor?
Sorry?
We're also storing the rank in the constructor, right?
Yes, but this is the rank. This is the rank of the tree. The invariant will then say that at this position we store the correct value. So we store the rank in the constructor, but we say we store some natural number in the constructor. Only the invariant says that it's actually the rank. So we have to define somehow the rank. Otherwise we could store arbitrary numbers there. Yeah, so we want to store the rank here. So now in the invariant, we say exactly that. So the first, this equation here is what answers your question. So the invariant ensures that we actually store the rank and not some arbitrary number. This is the this smaller than is the invariant for leftist heap. So the rank of the right subtree is smaller than the rank of the left subtree. And both children are leftist trees again. So sorry if I mix up leftist heap and leftist tree. I think it's called consistently leftist tree here. Okay. Any questions to the invariant? Okay. So the complete invariant is of course heap and leftist tree. So it must form a heap and this leftist tree property must be satisfied. Okay, now why do we do that? So first of all, we have this nice property. The rank of the tree is logarithmic in the size of the elements. Or as we write it, we have 2 to the we have to the power of 2 on both sides here. Yeah, so this can quickly we can quickly sketch the proof of that. I'll just sketch it on the board. So if we have a tree that has the form left and right, well, we want to show this. So by induction hypothesis, we know that the rank of right equals the rank of p minus 1. So we know that by the invariant. And we know that rank of left is greater than this, also by the invariant, so the rank of the left one is greater than the rank of the right one. So now we can start with the size of t plus 1, so that's what's written on the right hand side here. This index 1 always means size plus 1, number of elements plus 1. Well, we can insert the definition of size. It's left plus right plus 2. Now we can apply the induction hypothesis, which gives us an estimate for left plus 1 and right plus 1. So we will get zwar it broke. So we get 2 to the power of rank left plus 2 to the power of rank right. That's the induction hypothesis for left and right. Well, now we can have this, so we can estimate rank left by rank t minus 1, and we can insert this. So this rank left is rank t minus 1, and here we also get rank t minus 1 just by inserting this 1, and there we have what we want. So this is you can write it down as this in Isabelle, or you can use induct. Probably you can even use induct auto, and it will do it for you. So it's not that complicated to see that this holds. And in fact, this leftist tree may be very unbalanced. So, for example, for this example, this estimate may be much. This estimate may be quite imprecise actually, because you may have only one or two, rank 1 or 2 on the left, and here there may be an almost complete tree, so of any depth. So this leftist tree can get very unbalanced, but it does not harm. Okay. So now we can define merge such that it is bounded by the ranks. As we said, for merge, we all somehow have to insert stuff into one tree, and we can always arrange it to insert on the right, to do the insertion in the right subtree. And if we always do the insertion in the right subtree, we know that recursion is bounded by the rank. This is the main idea. So these are the these are the easy cases, and this is a complicated case. So let's look at this case here. So what do we do? So this node here is a so-called smart constructor, so first ignore it and just assume it constructs the node with root A, left L, and right this argument. So if we have to merge two nodes, if this node A1 is smaller, well, then we put A1 to the root, have the left here, and we merge with the right subtree of R1. So we merge this whole tree with the right subtree of R1. And in the other case, well, we put A2 to the root, and we merge R2 with this whole subtree. So it's essentially the same merge function as we had. But we have this node constructor here. And this node constructor does exactly this maintenance of the invariant by inserting. It has inserted. So this node constructor just swaps if the ranks got too big. So if the rank of the right subtree got bigger than the rank of the left subtree, well, this node function here will just swap the two trees and construct the tree with this one on the left. And the node constructor computes the correct rank of the constructed tree. So the node constructor just, if the ranks are the right way round, this is the swap case. So if the right rank is, sorry.
No, it's not swap case.
Yeah, I see, but I got confused.
Yeah, that's right. So the rank of the right subtree should be smaller, and then
Yeah.
we want-
But Why does the right, okay, that's why I got confused. This is a rank. I thought this was the subtree right that occurs on the left. Okay, this was my confusion. Okay, so if this is a non-swap case, so everything is in its correct order, and the rank of the new tree, well, it's the rank of the right subtree plus 1 as by the invariant. Otherwise, we swap. We swap right and left, and the rank, of course, is the rank of the new right subtree, which ought to be the left one. So that this is node constructor, just constructs the nodes, but swaps if the rank condition is not satisfied. And the idea is by swapping, you don't destroy the heap property and you don't change the meaning of the multiset. Yeah, so that's the whole idea of leftist trees. And the merge function, well, you can easily see that it's bounded by the rank. So whenever you descend to the right. You recurse, so the rank of R1 gets smaller, or the rank of R2 gets smaller than the sum of the ranks. So we take the sum of the ranks of these trees. Here, the sum will decrease by 1 because R2 has a smaller rank than this whole tree, and in this case, it will also decrease by 1 because R1 has a 1 smaller rank than this whole tree. So it's quite easy to see that the sum of the ranks decrease. So there can't be more recursions than the sum of the ranks. Yeah, so we can say the sum of the ranks decrease with every recursive call. The function package will see the sizes of the trees. So the pure termination argument is the sizes of the trees decrease. That's what I used in the implementation. But for the complexity, you have to see that the ranks actually decrease. However, yeah, so the ranks, I think it's even set up a way that you can actually show that the ranks decrease, but it's a bit hard to see it without having the invariant of the tree at hand. So that's a technical thing. The termination of a function, so you must show termination of a function without knowing any preconditions. The function must terminate unconditionally on every element of the type. So for every argument you pass, independent whether it satisfies the invariant or not, it just must have the right types. The function must terminate. You must prove that in Isabelle, otherwise the function package will not give you a function. And here it's easy to see that the sizes of the trees decrease. So if you define the size, for example, to be the cardinality of the multiset, the number of nodes in the tree, it's easy to see that in the recursive call this decreases. Well, this one has at least one more element than R1. But it's not that easy to see that the ranks decreases if you don't have the invariant. So it must still hold for arbitrary numbers stored there. Yeah, so I'm not even sure whether it holds. I think it holds because the former proof somehow managed to prove it in Isabelle, the former termination proof. But I changed it to the size because that makes the termination proof. But if you know that the invariant holds, which is all we are actually interested in, it's easy to see that the ranks also decrease. Because we exactly defined the invariant that the rank of this one is the rank of this one minus 1. Okay. Any questions so far? Yeah, so the functional correctness proof and preservation of invariant is actually straightforward. It's not much more than induct auto. So the complexity, so we already had this. And this gives us the complexities. So merge, we already said merge, the merge function in every call the rank decreases, the rank of the two arguments decreases. So of course we can estimate the time needed for merge then by the sum of the two ranks, plus 1, because we need the leaf case. And yeah, this gives us, if we do the logarithm on both sides, inserting this lemma here, then we get this estimate. Any questions so far? Okay. So then we can derive the other ones. So insert is just merge with a singleton tree. So we just merge with a singleton tree where we can construct a singleton tree in constant time. And then we merge, which is logarithmic time, so we get this measure. And delete min, well, this is just merge, the two subtrees. Well, and we have to we have to merge the two subtrees whose ranks are also logarithmic in their sizes. That's why we get a logarithmic measure here.
So we can get a better form, right? We can use log of t minus 1. Yeah, we can't define it, right?
I'm not sure whether we can get a better bound. Probably not. Or we have to we have the two subtrees. We have to merge them. So we will merge T1 and T2, and we know the rank. We know the number, the rank of T2, and we know the rank of T1. We can only use the size of the whole tree, perhaps minus 1, to estimate them. So maybe we can get a minus 1 here, but maybe not. But we are only interested in asymptotic bounds anyway. So it's O of log. It's O of logged size of t. So that's for this bounds. Usually we are only interested in asymptotic bounds. So even if you have to add some factors here to get the bound through, this does not really matter if we are only interested in asymptotic bounds. But actually it can happen if you try to prove such a thing or such a thing. If you try to prove such a thing by induction and you make this one too big, it actually can happen that your induction does not go through anymore. So just by being too unprecise, it may happen that in the inductive case you cannot do the estimation anymore. This can actually happen, so you have to be careful not to go too unprecise everywhere. Okay. So any questions to leftist trees? So these were leftist trees. So we have a nice logarithmic complexity heap data structure, quite simple to implement, quite simple to prove. What do we want more? Any questions to leftist trees?
Yes, regarding the termination proof,
Yeah.
merge,
Yeah.
you said it worked well without having to manually prove it, right? And why did you then show us the size estimate for in the next one?
No, we have to convince the function package to consider the sizes of the nodes. So it requires some convincing of the function package.
So you manually had to do it.
Yeah, it was. So I just told the function package, consider the size of the multisets, consider the cardinality of the tree as size, and then it worked automatically. But usually it would consider the size a bit differently. It would somehow say the size of a node is, I don't know what it defined there, something that did not really match. Okay. Yeah, so what do we want more? Well, the question is, can we perhaps use standard trees without any additional information? Just trees. Element, right successor, left successor, and keep them balanced. Without any management information at the nodes. Yeah?
In general or with that?
For heaps.
In general.
In general. We want to have heaps.
If you do binary, can do it. With the binary, where you would always have almost complete binary.
Okay, but this does not nicely work functionally.
Why? Because you descend the whole tree, then you insert, and then you have to bubble up. Usually it's not that nice, but.
Okay, yeah. So we will do something similar, to this. We will not exactly do binary trees, but the idea, the spirit may be similar. So we will say. We will use so-called brown trees. Does anyone know the brown tree data structure? Just out of curiosity. A brown tree says the number of elements in the right and left sibling must only differ by one at most. So it's not exactly this almost complete tree, but it's a similar property. So we say that if we have the left and the right tree, then we say that the number here and here must differ by at most one. And we also say which one is the smaller. So in order not to write it in the wrong direction, here now I will uncover it. So this is a brown tree. So if I have a tree and it has left and right, well, then I say the number in here must be smaller than the number in the left, but at most one smaller. This is the other bound there. So that's a very strong balancing criterion. I just say the number of elements in these in left and right must be almost equal.
And if they are not equal, only the right subtree is supposed to have less number. Is that?
Yes, exactly one less. So there are actually only two possibilities for this equation. there's either the possibility the two elements are equal, or there's a possibility the left is one bigger than the right. Yeah?
For proving, would it be better to write like this or write instead just no? So we say that either one case and the other case is true.
Good question. I can't actually answer which one is better. So maybe you end up in having to prove a lemma. Maybe you end up in having to prove a lemma for that. Okay. So as this tree is almost so all the trees have almost the same size. So you can also prove this logarithmic, the standard logarithmic dependency between height and number of elements. The proof is actually quite straightforward. So in the theories it goes by induct auto and one case distinction whether the height of the tree has fallen to 0. Okay, so we have to. The interesting thing is, why does this work? So why can we maintain, or how can we maintain this invariant of the right, left and right subtrees being related like this? So we have to think what happens if we add an element. So at some point we want to insert an element. Let's assume we have a tree. We have a heap, and we want to insert one more element, A. And let's say A is greater than the root node. Otherwise we just swap A and the root node and insert the root node. So where we have A is greater than the root node. So we have to insert A somewhere below the root. Where would you insert it? Left or right? Right. So if you insert A on the right, so then we get something like this, and we have element A here, then we can check what happens to the invariance. What happened to the invariant? Well, it's violated, probably. Right may be bigger than left now. Yeah?
I just want to say that there are essentially two cases. Either the A's are now equal or like this by one.
Yeah, there are only these two cases. So, but if we insert to the right, the invariant may get violated. But what if we insert to the right and then swap the two subtrees? What about the invariant now of this one? It holds. We can go through it. So we have to check that. I'm just writing down the invariant for this. We have to check that the new right subtree is less than or equal to the left, new left subtree, which is right plus 1, is less than or equal L plus 1. Okay, so left less than or equal R plus 1. just read it off up there. R plus 1 less than or equal L plus 1. Just read it off up there at 1 to both sides. Invariant still holds. So that's exactly what I wrote on the board. So you can just see this is two new equations that you have to prove, and you already find them here. Okay. We also may want to remove an element. So for this trees we will not implement we will implement delete similar to as we would do it on the heaps that you mentioned, these binary heaps. We will remove some element. Swap it, replace it by the top elements that we wanted to delete. So we remove some element from down the heap, put it on the top, and then let it sink down or sift it down until it reached a good position. So for this we need to remove an element somewhere from the heap. Not the minimum one leaf. We need to remove a leaf. So from which subtree would you remove the leaf? So we have this situation and we need to remove a leaf. Yeah?
From the left subtree.
Yes, exactly. So we remove the leaf from the left subtree and then?
Put it on top, then sit down.
No, but if we remove the leaf just on the left subtree, invariant may get violated again. Left may get too small.
Okay, I would first have sifted down and then checked it very. We can swap that.
Yeah. So it's exactly the same. Exactly the same. We move from the left and then we swap. It's exactly the symmetric thing. So we remove from the left and then swap, and what we get is these two new things. So the new right one must be less than the new left one, and this way round. So here I have -1 and +1 that cancel out. And these are exactly we can exactly, well, size left is less than size left -1 is less than or equal to size right. We can see it here, this equation, and this size right less than size left, we can see it here, so it still holds. So this is the idea of how to maintain the invariant in Brown trees. So we for insertion we insert to the right and then just swap the two subtrees. Yeah, so we can implement this on just binary trees. We don't need any maintenance information on the nodes. We implement no merge this time, but as I said, we implement insert and delete. Insert. How would you implement insert? Yeah, and if so you still have to, we have this heap and we want to insert an element A. So there may be two cases, yeah?
Yeah, either A is smaller, then we just insert it in right. If it's not, then we swap A and B and insert B in the right.
Exactly, yeah. So if A is smaller, then A gets a new root and B is inserted to the right. If A is not smaller, then we insert A to the right and keep B the root. So these are just the two cases. And that's exactly what this function does. So it, if a is smaller, then a gets a new root and we insert the old root to the right and swap. And here, the same way around. Here the other way around, we insert a to the right and swap. And again, it's quite straightforward to show correctness and invariant preservation here. So once you have intuitively, you have to get this idea why insertion is correct. And for Isabel, it's once you have this idea, perhaps it's one lemma and it's not too far from induct auto. Well, delete minimum element. How would you do that? Think of binary heaps from heap sort. Who knows heap sort? Heap sort of this binary heaps? So how do you delete an element there? The minimum element. Yeah?
Maybe swap it with the element in the lowest level, which is the most to the right, and then you shift down.
Yeah. So if you have this this heap here, and it may somehow, well, the lowest level may somehow have a gap. I don't know how to draw these things nicely. So these heap are always in levels there as they are stored in an array. And what you do is you take, you remove this element. So we make this heap one shorter here, meaning removing this leaf, put the value of this leaf to this node because you wanted to erase this node and not the leaf. And then you have a node that may be too big here, and then you start thinking it down. You start to think sift down or think procedure for this node until swapping it with appropriate predecessor nodes until it's not too big anymore. Yeah?
Yeah, but we cannot do it exactly like this.
No, we can't.
Because we cannot point to the last element.
Right.
We could down this one and that's really
But we can. But the idea is it's enough to remove any element out of the subtrees. It must not be this one.
No.
Yeah. So which element would we pick? So of course we don't have this layered structure. We don't have an array to index in here. So if we have this heap, left, our heap looks like this, and we want to remove B, so we have to pick and remove an arbitrary element from one of these two. Yeah. So you?
Root of the left. Root of the left subgroup.
We cannot remove a root. Removing a root node is always difficult. What to do with the children? Yeah. And what node is then effectively removed?
The leftmost.
The leftmost node, right. So we go to the left, go to the left, go to the left, go to the left, until we reach the leftmost node, and that is what we remove. And this also, removing the leftmost node is also consistent with our invariant preservation, because to remove things, we can remove it from the left and then swap. The invariant is preserved. And once we have done this, we have to do the sift down. So that's exactly what we do. So we remove the leftmost node, get Y and a new heap, and then we do a sift down of Y in the heap, well, we have swapped. After removing the leftmost node, we need to swap. Yeah?
Personally, I think that's too complicated. I think we can just use delete node and
Sorry, we can use?
I think we can just use like delete minimum first tree like we just said. I think when we do just delete the minimum of the right tree, that means we actually remove the root and get a new tree which is now without the root. But we know the root, I mean we can easily see the root.
So,
and then replace our root by the right root. Well, I think that should be possible.
let me try to sketch what you said, just to understand what you meant. So you wanted to do what?
I want to delete the min of the right tree because there is an element probably.
Delete the min of the left tree.
Yeah, exactly. Because that will be the root, won't it? I mean, when I delete the min of the right tree, then I know
So you can only delete the minimum of the left tree. Otherwise, you will end up with a violated invariant.
Right.
So you want to delete the minimum of the left tree?
Yes. Then
recursively.
Recursively, yes. And I have this root node of the left tree is removed, and I can replace like I actually want to remove my root of this bigger tree, and I can replace it by this or by the other root of the other.
Oh wait. So you delete the minimum of.
If you could maybe put 8 on that, maybe. Like the root node of this one could be maybe named whatever, and the other one B and the other C also. Yeah,
Okay.
So when I remove from the left tree the B,
yes.
Then I get a new tree which is already inspired, and then B is removed from that, and I want to remove A actually from my.
Yes.
So then I can put A, like remove it, and then I just have to pick B or C on the root there, I think. But I'm not completely sure.
Okay, so you somehow want to do the sift down and delete. You somehow combine the two. So wait, let's go through it. It's interesting. Perhaps it works. So you remove the B. So then you have the B removed here, and you have a new tree without the B, and you have the B here, and now you say you can just restore the heap property if it should be violated by swapping B with C. So B is definitely smaller than everything in here.
I'm not really sure because
B is because it was the minimum, it was the root element of the heap. So B is smaller than everything than here, and so if B is also smaller than C, everything is fine. But if B is greater than C, then we have to swap C, and C is smaller than B, smaller than everything in here, should work.
The right subtree.
What?
The right subtree is the problem, because so let C be like 2, and then C has 3 under it, and B is 4, then they cannot do this.
we have to sit down the B completely on this side.
Okay. Okay.
So yeah, B is not necessarily smaller than everything in the subtree under C.
So the problem is, wait. Now I'm confused. So
there is a case where B is larger than C, and also larger than some of the elements in the subtree of C.
there is a case where B is larger than C, yes,
and also larger than some of the items
then you would have to swap B and C and do the sift down anyway. Okay, yeah. So you end up with a standard sift down. Okay. Yeah. Okay.
But maybe what you could do is, because do we need and delete? Okay. If we would have implemented delete min with so that it returns a pair, then we could get rid of the delete left function because we always delete in the left subtree.
Yeah, but it does not. That's the question whether it's yeah. So let's go for this delete left sift down. Perhaps there are some variations. Yeah. So if I could, perhaps I could. You mean I could use delete min here instead of delete left, and then sift down. Yeah, this may work. But it would probably complicate the algorithm.
It only has to return a pair, so we only have to get the minimum 2 if we
Yeah, of course.
the only change we would have. This would change the whole interface, which would
You know, but I mean, maybe it would also complicate the algorithm because you would have to. Maybe not. I'm not that sure.
I think the runtime would be hard.
No.
Because you have to sit down like all the.
Oh yeah.
entries.
Oh yeah. You will get one sift down per level in the tree. This actually may kill your runtime. Yeah. You at least you have to be careful about this. Okay. Yeah, so we can delete the left, just descend to the left, and of course swap the subtrees. This was, we already ensured that the invariant is preserved by this. And sift down, it's a standard sift down that you know from heaps. So for a leaf case, you just have to figure out the right order of x and a. So this is a case where one is a leaf and the other is a singleton tree. And for 2 nodes, well, there are just a few cases that you have to consider, but I think the idea is find out whether to swap with the left or with the right subtree, and then sift down recursively. So let's try to reconstruct the standard idea before looking at this mess of code. So here in this situation, we have an element, so we have a name here, A, and this is x1 and this is x2. And the idea is we have A, x1 and x2. The idea is find the smallest of these 3 and put it on the top. So A is not the smallest. If A is the smallest, we are finished. If x1 is the smallest element, well, then x1 has to go to the top, and we can think down A. We can fit down A in the left tree. Otherwise, if x2 is the smallest of these 3, x2 has to go to the top, and we can think sit down A in the right subtree. That's the idea, and I hope that these cases are somehow covered here. So this case, the first case is that A was the smallest, so we do nothing. The second case is that x1 is the smallest. Then x1 goes to the root, and we have to sift down A to the left where it came from. where the x1 came from, and here in this metric case x2 is the smallest, so x2 goes to the root. Okay, so this obviously preserves the invariant because it does not change the structure of the tree. So it just swaps. So the structure of the tree remains the same, it just swaps elements. And the invariant only says something about the structure of the tree, not on what the elements are, only how many elements there are and where they are. So this obviously preserves the invariant. Yeah, and functional correctness, well, it's in the archive of formal proof. It's an AFP entry. You can have a look at it. Mostly straightforward, but it requires some lemmas to distinguish all these cases. Perhaps the proofs can even be refined if one puts some work on it. Okay, yeah. So the complexity is also quite easy to see because these runtimes are all bounded by the height. We always descend, and for recursion we always descend by 1 into the subtrees, and the height was logarithmic. Yeah, that's it basically. We can. Yeah, I have some material on sorting with priority queues. So we already did sorting with. First of all, any questions to this? First of all, any questions to these brown trees? Okay, so we can also use priority queues for sorting. This is more or less the same way as we used trees, search trees for sorting. So how would you sort with a priority queue? Yeah?
We have built a heap from the list and then just remove the elements after another and insert them into the list.
Yeah, exactly.
For certain trees, you can do the build heap intelligently, and this is more efficient.
Yes.
I don't know if this applies to the tree lists.
Wait for the exercise sheet. Yeah, naively we can build the heap. We can build the heap just by folding over insert, and then we can just remove the minimum elements until the heap is empty. So that's the naive way, and this one here can be improved intelligently. But the runtime will be dominated by this one anyway.
Yeah, for arrays that would be faster.
Not asymptotically. This is a n.
For binary heaps, it's faster if you do it in the good way.
Okay, but asymptotic.
Because it's n log n with
Yeah.
if you construct it naively, and if you don't construct it naively, it's log n.
But the sorting still is n log n.
Yeah, sure.
Yeah. So I said this phase here dominates complexity anyway. So from the whole algorithm remains n log n, but this array building up, and it's not log n, it's n, so it's linear time. So it cannot build up an array of size n in log n time. That's still just not possible.
Yeah, if you have the array already.
Yeah. So the complexity of this thing is n log n. So as is for heap sort. And here for our naive-minded heap sort or functional heap sort, or how you would call it, this is just we build the array by inserting. It's n elements that we insert to the heap, requiring log n time in worst case. And here we delete n, we recurse n times, and remove an element from the heap which requires log n time each removal operation. So that's an n log n algorithm. And that's more or less one of the ideas behind heap sort. The other idea, if you implement heap sort, the other idea is how to implement it that you can do it in situ sort. So how to you implement the heap as an array, then have this heapify thing, and then use this layered heap to remove and sift down. So this is the other idea. So this is more or less the basic idea, the high level idea. If you want to explain heap sort to someone, you would probably first start with more or less this idea where you build a heap and then remove the minimum element iteratively, and then you would go on, and there is even a really nice way to implement that on arrays. Yeah, so this is the one part. Okay. Any questions so far? I think then we are out of time and out of material. Thank you very much, and see you in the tutorial, where I think we have put it on the sheet exactly this linear time heap construction thing.
I have a question regarding the homework.
Yeah.
This time the homework requires us to import the try theory. So what should be the path for the import? Should it be the
It
same?
should it should work. It should work with any path actually. It should.
With the template now. With the template works now. Yeah.
Okay. Yes, it did not work because it's a bit strange system. It ignores the imports actually. I think it ignores it either completely ignores the import or ignores the path names of the imports. Maybe it does only ignore the path names of the import. I do not even know how the system works. And then it feeds it to Isabel with the right imports already set up. And what the right imports are, I have to tell the admin of the system. And if I don't tell him, then I get mails from you. It complains it does not build. So in any way, if it does not build for you, if it builds on your local machine, and you are sure that the theories that you import are standard theories, then I will probably be able to build it on my machine. Yeah.
Well, they're not standard. They're given as part of the course. They're not.
Yes. If they are given as part of the course, I have access to them too, right? Okay. Yeah. And I just have to adjust the path in worst case. In best case, use the path from the templates. So if you want a service to me, use the paths from the templates, because these are the paths that work for me on my local machine. So this is a bit. Will have to find a solution for the setup at some point to make it more standardized, but for now, yeah.
And it seems that we always have to name our lemmas if you want to put it in the homework, or else the system doesn't seem to do the check code.
If you don't name the lemma, the system does not. I did not know that.
I think that's what I thought for the past.
Okay, I did not know that. So I never used the system. Yeah, but as I said, as long as it builds for you locally, you should not be too worried about getting back an error message from the system.
Ich habe noch mal was zu dem, wenn man das, wenn delete min so ein paar machen würde, dann könnte man ja sift down einfach anders implementieren und sift down siftet sozusagen nur ein Level runter.
Ach so.
Dann würde es ja wieder gehen.
Aber
so.
Du kommst immer noch.
Also es macht es nicht schneller, aber.
Nein, du kommst immer noch in das Problem, was wir hier hatten. Wenn du delete min hier gemacht hast, dann kriegst du ein B hier, das ist zu groß. Und das B hier musst du im Worst Case bis ganz hier runter shiften. Bis ganz hier runter sinken lassen. Das musst du und ich sehe jetzt gerade nicht, kann sein, dass es nicht muss, aber wenn du das Recode unter sich machst, musst du das im Worst Case in jedem Level machen. Und das könnte zu viel sein.
Wir machen das auch hier. Sorry, we're also shifting it in our definition. for every subtree.
We go one time down to find the leftmost element. That's clearly the height of the tree.
Right.
And once we have found the leftmost element, we go another time down to think the element.
Yeah, but
this is also the height of the tree.
not necessarily on this side, right? We're going down on the whole tree.
Yes, but only one path.
Ah.
So thinking an element only follows one path in the tree.
Right. Okay.
And what he proposes, merge so delete min recursively, so we may get a whole path in this tree, 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 and I just can't see whether we can really get it or not. So maybe you can somehow estimate that we don't get it.
No.
Yeah, bound up.
By the way, you're still recording. You're still recording.
Oh,
You're still recording.
Thank you. I will stop.